All right, so hopefully you're still with me. Let's go through the actual settings on here now. The resolution exponent, as you can see here, roughly corresponds to how detailed the surface is. What's actually going on here is, as I explained to you a minute ago, all of those component waveforms, they are stored in these voxel grids. So you can see now the amplitude is 4x4. It's really a two-dimensional grid, so you can ignore the y1. But in any case, so frequency is 4x4, because that's what this is squared. If this is 5, you'll say 2 to the 5th power is 32, and so on. It basically is saying you can have this many component waveforms. So the more component waveforms you have, the more detailed it ends up being. Now we can still only capture these if we have enough resolution on our thing here, but at render time we can always dice it to the resolution we need. So you can see how much detail there is now. An incredible amount, maybe even too much. You don't always want to have an incredible amount of detail. I mean, think of a pond or even like a gently moving lake. It doesn't more detail is not necessarily better here. It certainly makes it slower. It'll be faster with less, as you can see. There's just a lot more to do. But at 10, we now have 1,000 by 1,000 essentially things. There's just a lot more waveforms to reconstruct into our final thing. I mean, if you need it, you need it, and it's obviously not that bad. But the point is, don't just arbitrarily do it. For our purposes, I'm going to go down to 9. As a side note, an interesting thing, if you look at the spectrum itself, it has its own visualization tab. If you go to spectrum, you can see this. What is this that we're seeing? This is the fast Fourier transform again. I keep trying to get away from it, but there it is. It's showing you, it's plotting the data that's being stored. If I have less resolution again, there's less data. And here we are back to that again. Each point here is representing the center of a voxel, and it's storing the various components of the wave, all the information. We're definitely not going to get into that granular detail, but it's storing all the little settings per wave on here. So the more resolution we have, the more component waveforms we have. And as we get out here, it starts to look like this, where the biggest waves, we're seeing down here. We're getting lots more small waves, which are looking in this visualization like green apparently. So we still, even as we have more resolution, we're not getting more and more giant waves. We're getting more and more smaller and smaller waves. So they all start to kind of look the same after a while out here. But that's what this is. This is like an oscilloscope or maybe a spectrograph or something that's plotting different kinds of waveforms in a way that a human might be able to comprehend it. As we change, various settings around on here, you'll see the numbers change. You'll see the values change on there, especially if we change the direction, you'll see them change. This is for debugging, this is for fun and things, but we don't probably really need to see that. But there you go. This is what you get for watching a Applied Houdini video, is I'm going to tell you the nitty-gritty. So coming back to this, what are these actual parameters that you're actually interested in? Well, we got the resolution at 9. Grid size is easy. Grid size is the size of the unique size of a wave area. So at 50, this grid is 100 by 100, right? So if the wave pattern is 50 by 50, that means we should see it duplicating, and we do. If you look closely, see this kind of V-shape area here? There it is again. You can spot them if you look out, or honestly, you could just make the grid size smaller. And the smaller we get it, the more the repetition becomes abundantly clear. Now we'll do a lot to mitigate the repetitious pattern. I mean, it's already kind of hard to tell anyway. It's not too bad, but it is there, and that's what the grid size is. So this is an artistic control. It's not based in physics or anything, but it might be an easy way to address notes or to get to a certain look faster. Grid center, as you can imagine, is just offsetting it in space. If you wanted to have the boat start maybe in a certain area of the waves, you could do that. Depth, as near as I can tell, does nothing. It has a description of what it does. You can read it. I have never had it do anything. I mean, you can bring it to like incredibly high numbers and nothing happens, and incredibly low numbers and nothing happens. So near as I can tell, it doesn't do anything. Gravity is one that is kind of fun. The lower you make gravity, you'll get higher, slower moving waves. Because without gravity, the peaks of these waves have no reason to come back down again. That oscillating motion of the waves getting bigger and then being pulled back down isn't really happening if there isn't anything to pull it down. So what you end up getting is very slow moving large waves. There's other ways to do that. Don't do it here. I mean, what are you doing? Unless you're doing Interstellar or something, where you're doing an ocean planet where the gravity is different, don't mess with the gravity. Seed, of course, will randomize where the waves start off. It actually can give rise to some pretty different looking results, which is kind of surprising. You know, with all of our other parameters not changing, you'd think that the seed wouldn't change things that much, but it actually kind of does. Keep it at 0. Time offset, self-explanatory. You know, it's where we are in time. Time scale, kind of self-explanatory as well. You know, you can make the waves go by much faster. Probably shouldn't do that. Again, things like that should be done by the wind speed and stuff, but if you really, again, just needed some artistic control, you could alter it here. Loop over time is not useful to us. Loop over time is very useful to people designing oceans for video games, or if you wanted to make a looping graphic, then it's super useful. Basically what it says is, without it, you know, the ocean just goes. With loop over time, it ensures that it ends up in the same place that it started every this many seconds. So if I were to make it be 5 seconds, because we know our shot is 5 seconds long, it will start in the same place that it ends, as you can see. It'll move along the way, but it's clever that it will blend back into where it started from by the end of that time period. If I made it to be 1 second, every 24 frames, it will look exactly the same, like you can see. But in between those 24 frames, it doesn't even get a chance to move that much. It doesn't get enough chance to blend. So you just end up with a weird looking ocean that just has little small waves moving across large waves, which could be interesting, I guess, but we're not using it today. Now, the main event. Direction, speed, and chop. These are all the ones that matter the most. Direction is how many degrees around the y-axis it is oriented. Currently, they are actually moving in a direction, as you can see. They're moving along the x-axis. Let me click this. There you go. They're moving along the x-axis. If I wanted to change that, I can, rotate these things. So here we go. Now it's rotating at -50. So now it's kind of moving to the lower right-hand corner, which is nice. I kind of want the waves to move against the boat a little bit, or a good deal rather, but to be at a little bit of an angle to it. So that's nice. Speed is one of the most important ones. Speed is not just, in fact, how fast it's moving that direction, although it is part of it. Speed has everything to do with the distribution of wave sizes. The higher the speed gets, the more large and higher waves you get. So here was like the North Sea, or the North Atlantic kind of crazy storminess. A very high wind. That's what makes waves in the open ocean, is wind. So having the high wind means we get these big dramatic waves. But check this out. On the other side of the equation, that's true too. The lower we make this, the less we get, and the more we see the small waves. So dramatically different, just based on the speed itself. So now we still have wind, but it's just blowing, little disturbances on the surface. And obviously the lower you get it, the less and less we see. I think if you go to 0, it gets confused. It just goes the other way and makes the maximum. So we started at 5, I think. Yeah, it's the default. And so if I go, you know, what we're doing here is an ocean flat tank. This is flat tank sim. We're going to blend a flat tank flip simulation, which is just starts with a flat surface. We're going to blend it back into an ocean that is not technically flat. We'll never be able to get away with blending into this. You know, I mean, look at how the waves cover the boat, you know. Now, ocean, you know, there are different kinds of ocean sims, and we're only talking about the flat tank one here. But the flat tank one here is by far the most commonly done one in movies and TV and stuff. Because what it's used for is to do boat wakes, which comes up a lot. Boat wakes and any other like general disturbance of a lake or whatever. You know, something being thrown into a lake or into a pond or into a puddle. You would all use this setup. And it's the most common stuff. So it doesn't really work with this, but you still get to do some. If it's at 5 by default and I go down to like 3, we still have waves, but this is acceptable. We could blend back into this. It's not deviating so much that when we interpolate, you know, when we blend between our flip sim and this ocean, it'll still be quite believable. This is flat enough for our purposes. You might even be able to get away with a 5. But 3, just for what I want to do today, will be fine. Not all the waves are moving in this direction. If I go down to directional bias, the more we do this, the higher we make the bias, the more it ensures we are all moving in that direction, which is not bad. This is a certain look as well. It's nice to have it be kind of low, though, where they're not all moving in that direction. Some of them are deviating a little bit. You could, in fact, go all the way down this way, and now they're just, you can see there is no direction. They're all kind of just going in their own way. You might see this. You might see this in a storm, or like where a bunch of rivers converge on each other, where it's just chaotic motion. But usually artistically, it's nice to at least have some sense of direction. So I'm going to keep that at 2. Directional movement is the same thing, more or less. You can have this. It affects which waves are affected by the directional bias. I'm just going to keep that. They don't really use it that much. Chop is the last main thing. Chop is how sharp the waves are. So you can see the higher I make this, the more it sharpens the peaks here, like so. If you were making a less windy area, you'd probably also want to bring the choppiness down on it. I'm going to keep it at 0.7 for now. Similarly, I should mention, if things are less windy, you know, like down here, you probably don't need as much resolution either. So you could probably bring the resolution down a good deal. Because you don't want to have like necessarily a million little waves when it's not windy. It would depend. But I'll keep that at 9. I'll keep this at 3, which I think is what it was at. And there you go. So there you go. We got to the main settings of the spectrum.